And the first hour is on a new construction on the modular space of pointed rational curves.
Yeah.
The second hour will be on a topological recursion for higher genus curves.
Right. Yeah. Thank you for your invitation. So I will start from the moduli of rational curves. So maybe many of you already know of beta plane. Yeah. Modular space of pointed rational curves. Yeah. So first, I will talk about smooth case. So that means a pointed P1. N pointed P1. So let me start from M01. M03. So that's the 3 point on P1, and we want to classify the object. So let me write down what it is. So moduli of, let me say P1, or maybe, yeah, smooth genus 0 curve, which is a P1 with with 3 marked point, 3 distinct marked point. And then you want to say that, triple will be same if they are, mapped by the PGL2 or Möbius transform. Or automorphism of P1. It's the same thing. All of 3 are same thing. Same object to say different way. So let me write a picture. So you have P1 with 3 marked point. Say P1, P2, P3. Then if you take the affine coordinate, the P1 has a C inside. P1 is a C plus or C union with a 1 point. So you can take C inside. I should say everything is over C. So you can take affine coordinate is x1, x2, x2, x1, x3. Then you run in complex analysis, you can send 3 points to the 0, 1, infinity. So you can always, send, let's say P1, P2, P3 to 0, 1, infinity by an element in whatever those are, automorphism of P1. How do you do this? What the explicit map is. So what the explicit map is, you want to send x1 to 0, right? So if you take x minus x1, if you plug in x1, you will get 0, right? So this is a numerator. And if you plug in x2, P2's coordinate of P2 is x2. So if you plug in, P3, If you plug in P3, you want to get infinity. So if you take x minus x3 as a denominator, you will get 0 in denominator. So you will send to the infinity, right? And then if you plug into x2, you should get 1. That means you will you will multiply by x2 minus x3. So if you plug in x2, you will cancel this denominator and this guy. And then you will take x2 minus x1 in another denominator. Then if you plug in x2, you will cancel this numerator and this denominator. So you will get 1. So this is a map which sends P1, P2, P3 to the 0, 1, infinity. And we will write down this map by lambda x. and it will be, this map will be called cross ratio. That's what you run in the complex analysis. Well, you will run. I don't know how when you will run, but now let me go up to one more point. So let me do the same thing for 4 distinct points. So this time you have 4 points, and they are distinct. So this time you have another point. Let me write them by red. So x4. So same thing will happen as M03. So you have P1, P2, P3, and P4. Okay. Then you can send first 3 points to the 0, 1, infinity, and last point will be lambda x4, right? You send, if you want to send P1, P2, P3, you will, plug in this this function, so you will get the fourth point will be this guy, so that you will get lambda x4, which is in the P1 minus 0, 1, infinity. Because P4 is different from x1 to x3, so they never send to the 0, 1, infinity. So that M04 is, this means M04 will be isomorphic or equal to P1 minus 0, 1, infinity. Right? And then later I will denote 0, 1, infinity as D, large D, which is a divisor, not connected, but a divisor on P1, so that you want to avoid, I don't know, it's the right time to say it, but you want to avoid other point to come here, so you want to take the wonderful compactification with respect to D. That's how you construct M bar 0n. If you, so, okay, yeah.
Wonderful is a technical term.
Technical term, yeah. The Italian people call, yeah. That's the continue and projective who names it. And you can construct M bar 0n as a wonderful compactification. That's the first talk, yeah. Okay, so let me go to M bar 0n. M0n. M0n, which is now same thing. With now moduli of smooth genus 0 curves with n marked point. With n distinct marked point. So now, same thing, so how can we construct this guy? So we have now P1 with P2, P3, P4, and Pn. Now we have n point. Then if you send by, we will do the same thing. So we will send P1, P2, P3 to the 0, 1, infinity. So you will get P 0, 1, infinity and 0. Okay. 0, 1, infinity and lambda P4. Maybe I should write down lambda x4, lambda Pn. So that those lambdas x4 to, xn, x are the, so P is a point, neighbor point, and x are the, maybe coordinate, I should say. Then you can see those guys will parameterize M0n, right? I mean, the first 3 points always go to 0, 1, infinity. So this guy will be isomorphic to M bar. I mean, oops, maybe I should write that this way. P1 minus D, that D was 0, 1, infinity, cross P1 minus D, and minus all the diagonals. Right, this is M bar 04 because I mean lambda xi will be the element in here, and you want to avoid those guys will be same, so that you have to subtract all diagonal. And if you see this, and if you know wonderful compactification, you will do at first wonderful compactification respect to D, and then after that you will do wonderful compactification respect to diagonal. Then you will get M bar 0n. And if you are a specialist, I can stop here, but maybe I should explain more, right? Okay, so the second section is limit. So if you want to compactify, you have to define the limit of the elements. So let me give one example. So if you have curve with 4 marked points, which is P1 with 0, 1, infinity, and T, and another family of curve is P1 with 0, T inverse, infinity 1. And let me consider those. And I have to make a remark that T is of course different from 0, 1, infinity. So they are different from 0, 1, infinity. So those are the elements inside of M04, and we want to take a limit. So let me take, before that, let me show those two guys are same in elements of M04, because if you take what's the cross ratio of CT is already first 3 points go to 0, 1, infinity, so the cross ratio is T. And how about dt? What's the cross ratio of dt? So we want to send 0 T inverse infinity to the 0, 1, infinity, right? So if you multiply Tx, then you will plug in 0 here, you will get 0. T inverse here, you get 1. And infinity times T will give you infinity. So this guy will send to first 3 points to 0, 1, infinity. So that the cross ratio by Tx cross ratio will be T times 1, which is T. So that both family has same cross ratio. That means Ct is equal to dt inside of M04. But if you take T go to 0, what will happen? If you take T go to 0, so let me write. If T go to 0, then you will get, so in that case, P1 equal to P4, right? But if you take T go to 0 here, you get P2 equal P3. So the middle guys will be same. And those are different stuff, right? So you have to do something. So what you will do is, so good way way to compactify M0n is introducing instead of smooth curve, you will introduce stable curves. I mean nodal curves. Sorry. So that is not what is maybe instead of smooth curve. So let me explain what the, maybe I should write down stable instead of nodal. So let me so what's the stable genus zero curve is that's a tree of P1. So stable genus zero. Genus zero stable curve. Curve is a tree of P1. So you have just tree of P1. That means there is no loop with all intersection and all intersection sections are nodal point with stability condition. And stability condition is following. So they have the P1, each P1 has at least 3 special points. And special point means the nodal point or marked point. So let me do the example which I gave before. So you have CT, which is 0, 1, infinity and T. P1, P2, P3, P4. And you have dt, which is P1, P2, P3, P4, and 0, t inverse infinity, and 1. Then we will take limit t go to 0. So in the first case, the P4 go to P1, but in that case, the stable curve which will represent limit of this guy will be P1 and P4 will be at the same P1, and P2 and P3 will be the same P1. So how do you think about this is if P4 approach to P1, you will bubble off another P1 and then put the P1 and P4 on the new component. And the way how to put P1 and P4 does not matter. The reason is you have 3 points in here, right? So you have this point, and another point. So you have 3 points on P1. So all the time you can send to the 0, 1, infinity by the automorphism of P1. So the way, the place where you put those 3 special points doesn't matter. So you can forget about, you don't have to worry about where to put. And the same thing, you can do same thing here. So P2 will approach it to P3, then you will bubble off another P1 at the infinity. Then you will put P2 and P3 on the same component. And then this time you will get P1 and P4 and on the same component, and P2 and P3 will be same component, and the limit will be equal. So this is a good, one of the good compactification. And it's wonderful actually, so maybe I should write down wonderful instead of good, but anyway. Okay, so now let me record the blow up. Blow up C2 along origin. So I don't want to talk about the, how can I say, general blow up, but let me talk about the first blow up you will learn in algebraic geometry, which is a two-dimensional case with, smooth two-dimensional case along the point. And so you have C2 and also the origin, and then you want to segregate the normal line. So you have, let me draw the picture. So you have C2 and you have two lines, line 1 and line 2, and you want to segregate L1 and L2 somehow. So the passenger is blowing up at the intersection point. And let me blow up space of 0, 0 of C2, which will be defined by maybe xy, xy cross z1, z2, which is the element inside of P1, A1, maybe C2 cross P1, which is x times z2 minus y times z1 equals 0, which is the same thing as determinant of xy z1, z2 equals 0, right? So this is a hypersurface in three-dimensional stuff, so it will be the two-dimensional. So let me consider the, and this map is just projection to xy. So this map will be take the first two component. Projection of projection to C2. And let me investigate what the pre-image of point on C2. So if, oops, doesn't work. So if x and y is not equal to 0, origin, so what will happen? Let me write down instead of AB. So if you specify A and B, so you have A z2 minus B z1 equals 0. So that you can write down z2 equal, maybe I don't need to change, but from this equation you can find the ratio of z1, z2, so it will determine the only one point, so that the pre-image of AB will be a point, right? But if you have AB equals 0, then the equation will be 0 times z2 minus 0 times z1, which is always 0, whatever the z1, z2, so that then 0 times z2 minus 0 times z1 equals 0, so that pi inverse of AB, I mean, maybe I should write down 0, 0. 0, 0 will be whole P1, right? So far what I say is just if you have point except origin, then pre-image is just 1 point, and the pre-image of origin will be P1, and I don't say the two lines will segregate yet. So let me show they will segregate. So let me erase here. So now let me take, let me try to use another pen. Yeah, this work. So let me take a point T, MT, which is a line, I mean point in line, I mean point on line with slope M, right? Which goes to the origin. And then we will take the inverse image. So pi inverse of T times MT will be, let me just write down the equation. So this is the equation, and you can, if T is not 0, you can divide. So that pre-image will be, if you take Z1 equal 1, then you will get M for Z2, right? So you get 1M. So if you have wait, 1M, right? So if we take limit, so oops, not 1M, sorry. I should write down more precise. T times MT cross 1M. That's the right way to say, sorry. So that if you take T go to 0, limit point will be 0, 0 times 1M, right? So that slope of L1 is M1 and slope of L2 is M2, then their limit, the inverse image of, how can I say, inverse image of line which go to the limit point will be 1 M1 and 1 M2, so that they will be segregated. I don't want to, I should not say inverse image because they are not real inverse image. They are just taking the inverse image above the C2 minus 0, and then you take the limit, then you will have two different points above the origin. That's what I mean. So they can segregate if you have different slope, right? Okay, so this is just explanation for a blow up. And now let me explain the construction of M bar 05 and M bar 0, M bar 04 and 5. Maybe I should write down already. I missed to explain M bar 04, but. So let me say M bar 04 and M bar 05. So we say already M04 will be isomorphic to P1 minus 01 infinity. And if you want to take 4 points on P1, P1, P2, P3, P4, and 01 infinity and X, the first thing you can do is, already we saw, but you can take first point to first point. If you approach X to the 0, so you will get P1, P4, and P2, P3. So this is the limit point. And another limit point is if you take X to 1, you will get P2, P4, and P1, P3. And another one is you can take x to infinity. So you will get P1, P2, and P3, P4. So you will have 3 limit points, right? So that you, and all those guys will correspond to P4 go to 0, so this should be 0. So this one is P4 go to 1, so we should call this one is 1. And this one, for this one you will take P4 go to infinity, so maybe I should write down this way, the other way. P3 and 4, and 1, 2. So fourth point go to infinity, so we should call this guy as infinity. So you have 3 missing point and 3 limit point, so that you will, I mean, this is not a proof, but you will be convinced m bar 04 will be P1. And then let me construct P5, I mean m bar 05. So before that, let me construct the universal family on m bar 04. So universal family means each point will correspond to the curve which appear on m bar 04. So that, I mean, how to construct is this is you have, I mean, m bar 04 is P1, right? So you take P1 and you have 3 special points, which is 0, 1, infinity, and you take product with another P1, 0, 1, infinity. So you have product space, and you have, maybe change the color. Pullback of 0, 1, infinity, and the horizontal line for 0, 1, infinity. And so if you take curve here, whatever the point x, you have smooth curve with 3 marked point, but you want to have 4th marked point, right? I mean, you want to have 4 points. So you will take, I don't know, purple will work or not, but you will take diagonal section. Then you have 4 points, the purple point and 3 red point. So you can call this is P1, P2, P3, because always if you have 3 points, you can send to 0, 1, infinity, and then diagonal will give you 4th point. But there are bad things happening, because around 0, 1, infinity, I mean, along 0, 1, infinity, this line, and this line, and this line. So those 3 lines, you have 4 points, but the delta will be on the same point as a 0, 1, or infinity. So that's not good, right? They are not distinct. So what you have to do is blow up along those 3 points, because delta will coincide with 0, 1, infinity, right? Then after blowing up, you will have P1. So let me take the fiber of P1. So you will blow up at 0, 0, and 1, 1, and infinity of P1 cross P1. Then this will be the universal family, which I will denote m bar 0, I mean U04. U04 will give you the universal family on m bar 04. Let me take the fiber of 0, 0. So you blow up this point, so you have 2 P1, and 1 to infinity is original P1. So you have 1 to infinity here, which means the P3 and P2 and P3. And then new P1, which appear by blow up, will give you two point because purple line and red line have different slope, right? So they will be segregated. So you have 0 and also purple line which is fourth point, maybe write down x. So you have P4 and P1, and which is the same picture as this guy. So that over 0 you have curve which correspond to 0. So that that will give you the curve which we want, and you can do same thing for 1 and infinity. So that the blow up of 3 point, blow up P1 cross P1 along 3 point will give you the universal family. And actually this universal family will be M05 bar. And then you will suspect if you want to have, if you construct M bar 0n, you can do blow up, you can blow up P1 cross bar 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 P1 along the smooth subvariety. So how shall we do this is following. And let me give one more remark. So this is irrelevant, but the remark is M0n bar will be universal, n plus 1 will be universal family of M0n. And I forgot to say, but this 0 will represent the genus 0, and the second number will represent the number of point. I'm sorry I forgot to say that, but anyway. And then, so how shall we construct M bar 0n is following. So let me write down this. So this is a paper by Bomsik, Kim, and myself, and this is very, not very old, but old, 2009 in selector mathematics. So, and two-step wonderful compactification. Whatever it is, whatever the wonderful compactification is. I want to explain what is a wonderful compactification, but the wonderful compactification gives a new way of construction of M bar 0n. So recall, so M0n was following. So this was P1 minus D, where D was 0, 1, infinity. That's a smooth, not connected, but it's a very nice divisor in P1. And you will cross P1 minus D n minus 3 times. Okay, so let me write them by red. So this is n minus 3 product. And then you subtract diagonals, which I write down this way, delta I, where I is a partition of number 4 to n instead of 1 to n minus 1, whichever you want, but take 4 to n. That means, let's say, so example is, let me explain the delta I. They call polydiagonal, but so if you have 4 points, so you may have 1, 2, and 3, 4. Cardinality of I, if cardinality of I equal 4, or n equal 4, but maybe I should write down not this way, but maybe 1 to n minus 3, sorry. 1 to n minus 3. So this means the first component and second component will be same, and third component and fourth component will be same number. I mean same component, so that many people call this kind of stuff as a polydiagonal because not only one guy, but there are many many components you will take same numbers. So this is the open part, right? So how do you compactify this? So you will see bad part is this divisor and also the polydiagonal. And what you will do is at first you will blow up all the diagonal. So what you have to blow up is first the divisors. So starting, so at first you will start from, so at first you will close, you will forget these. So you will take the P1 with n minus 3 times. Then you will start blowing up. So blow up these. So first step. So at first blow up along D cross D cross D. Then the next step is you will put P1, one P1 in the component, and then you will take two P1 in the component, and so on, 3 component and 4 component, and if you get all of the component, you can not blow up, blow up doesn't change, but you will take this guy, and then second step is now blow up diagonals. Now second step. So each point here will parameterize a point in P1, right? n minus 3 point in P1. So you want to avoid those points coincide with D. So each, if you blow up those, your point will be away from D. That is 0, 1, infinity. Now you want to segregate those points will be different point, right? So now we will blow up now polydiagonals. So in this case, you can blow up many different way, but the one way to blow up is minimum to maximum in inclusion order. In inclusion order. So the smallest one is all the component or all the coordinate are same, and second one is all except one component is same, and then you will blow up in the inclusion order, but in some point you will have there are two polydiagonals which cannot compare, but both of them are minimum. Then those, whichever you want to take is, whichever you can start, whichever you can blow up first and second, they won't change any resulting space. So in this way you can get the resulting space will be is m bar 0n. So how do we, so now if you blow up around D, the polydiagonal, your point will be segregated. So that should be m bar 0n, right? Anyway. And so is this the new construction or not? That's another point, but due to the wonderful compactification, theory of wonderful compactification, this is exactly, equivalent to Schoenkeil's construction. So there is a paper by Lee which says if you have the subvariety of subvariety, then if they are building set order, then you can blow up nicely, then you will get a wonderful compactification. And if you have wonderful compactification once, then you have the subvariety, right? And then you can blow up minimum to maximum inclusion order. The result will be same. So, and the first, so you have bunch of subvariety in the P1 cross P1 cross P1, and the first thing what Schoenkeil did is his order is inclusion, building order. He proved that is, he didn't, but what he say in the modern language or wonderful compactification language, Schoenkeil's order is building set order. So from that, inclusion order will give you same construction, so that you can construct M bar 0n in this way, which is more,
It only blows up dimension 2 subvarieties, right?
Yeah, but he did in the, how can I say, inductively, right?
Yeah.
So that he starts from P1 with D and, which is trivial, but, and he take product with P1, so like that. So, but if you embed that guy in the P1 to P1 with n-3, it will not be the codimension 2, but if you restrict, it will be codimension 2. That's the thing, yeah. And what we did, what I did with Bomstrick is we constructed, we are not intended to construct M bar 0, and we wanted to construct the relative Fulton-MacPherson space, which Bomstrick used that space to define the Cauchy map space, so that we are not. So we write down this, this stuff in 3 lines, and maybe nobody read it, and then, right? So the title is Generalization of Fulton-MacPherson space. That's our title. And we constructed. And Bomstrick said next paper, so we construct a Cauchy map space by using generalization of Fulton-MacPherson space, and this was just 3 lines. So, and then, so nobody read it. I think nobody read this part probably. Nobody care about this part. Many people want to study Cauchy map space right now, right?
What space is that?
Cauchy map. That's how can I say, generalization of admissible covering space, or yeah, you will learn probably in a few years. And then 2013, I computed the Chow motif of generalization of Fulton-MacPherson space, and then somebody, Taba actually didn't read our paper, and he claimed this is his construction, and he computed the Chow ring of M bar 0n. And then he computed this, how can I say? He claimed Chow ring of this construction is much simpler than Chow ring of, Chow ring representation of Schoenkeil, but I don't see the difference because they are just different kind of wonderful compactification by same subscheme, so they should be same.
So he's claiming that this way you obtain a different presentation of the ring, so different generators.
Different generator, yeah.
Is there some geometry in this generator still?
Oh, generator is just these. So every guy will correspond to the divisor class in the M bar 0n.
Every exceptional divisor.
Exceptional divisor.
Divisor is named by Williams something.
Generator with a generator from P1 to P1, I mean P1 cross P1. So basically Chow ring, I mean Chow or motif of P1 cross P1 with, Chow of n minus 3 and all the divisor which, expression divisor which correspond to those. And if they are nested, you will have intersection, but if you are not nested, which means this is nested, right? This is nested from here. This is this is nested inside of here, right? If you take intersection of, with this kind of stuff, this guy is inside of intersection of those, right? But in the polydiagonal, it won't, right? If you have 1, 2, and 3, 4 come together, so let me write. So let's say 1, 2, and 3, 4 come together, which means that in the picture, 1, 2, and 3, 4 come together, but the 1, 4, and 2, 3 come together. Oh, this guy will be nested. Sorry, I didn't prepare. So 2, 3, and 1. This is not nested. Sorry, this is not nested, right? You cannot. So the intersection of those two guys will be empty. So you will divide by this. Not nested guy. Not nested. That's also from the general theory of wonderful compactification. So you don't have to care. You don't need to learn anything besides wonderful compactification. If you know the wonderful compactification and their result, even you don't understand the proof, you can write down the generator and the relation. So
you just claim this is a certain presentation.
No, yeah, he is. I'm not claiming. Yeah, he is.
Does it give any reasoning for why this should or could be?
I don't know.
When you say it's like you're still blowing up along the same subscheme.
The same something, just the order is different. So,
That's interesting.
and he claimed this construction is new construction, but I don't think, And also you can construct the Angela Gibnelli and other people's projective tree, modular projective tree by the generalization of Fulton-Maxwell space. So you can compute the Chow motif or Chow ring of that space by wonderful compactification technique. So, yeah.
Sorry, when you say generalization of Fulton-Maxwell, you're talking about
configuration space, right?
Still on P1 or
no, X. Projective smooth projective space.
Right.
Yeah. So basically, so Fulton space does just the second step, right? So we just put the sub-scheme, to avoid the point go to the sub-scheme. So you have to blow up, but it's easy, how can I say? It's easy to prove this is building order because intersection is very nice and so on. So, if you have, if you replace X by, if you replace P1 by X, but the intersection of those are ridiculously easy. So, if D is smooth divisor, so that you can prove this stuff. This subscheme has a building order, so that blow up this way will give you wonderful compactification. So, okay, so the first part is this much. So.